Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and we were continuing from our previous module. We were discussing how to find the moment or the inertia tensor, and we will right away start with some examples in this module. So the topic of discussion is the inertia tensor. The inertia tensor, right? And the example that I have is a uniform rectangular plate has mass m and sides 2a and 2b. We need to find the inertia tensor. Find the inertia tensor at points G and C. So the setup is we have a plate, and the moment of inertia we have to find. So at the center of mass, and so this is the point G, which is the center of the plate or the center of mass, and the second point C is at one of the end points or the vertex. So let us now associate an axis. So we have x1, x2, x3 axis, and so if we were to find the inertia tensor, so let us find the the moment of inertia. So we see that about the center of mass axis, the moment of inertia is given by I11 is MOI, which is about the gx1 axis, and so this is along the x1 axis is our principal moment of inertia or the principal inertia component, and similarly I22. I have to associate some dimensions here. So the dimensions are 2a and 2b, and we see that I11 will be equal to half mb square. That's the perpendicular distance from from the axis OX1 or GX1, I would say GX1, and similarly I22 will be I think this factor is 1/3, so I22 is 1/3 ma square. Again the perpendicular distance is will be ma square, and then similarly we can find out that ij, the off diagonal moments for I not equal to j is 0 for all ij, because we are talking about the rotation about the principal axis here, right? So all the off diagonal moments are 0, and we see that so what we get is that m x2 x3 is summation m x1 x3. This is 0. So what happens is the plate is 2D, because the plate is 2D at with x3 is very thin. So the dimension along the x3 axis is very thin. So we expect that all these off diagonal moments are 0, and also we expect that the first off diagonal moment m x1 x2 will be also 0, because there is a symmetry about this axis OX2. So we have a symmetry symmetry about G. Okay, so then what we have is, so about point C, about this second point C, right? So about C, we see that I11 will be 1/3 mb square, plus we have an additional distance b. So we use our parallel axis theorem. So from OX1 we have a perpendicular distance b, so we add this second quantity mb square. So this is from parallel axis theorem. Okay, so we get that this is also equal to 4/3 mb square. And similarly I22 will be 4/3 ma square, and so on. So we see that our from I11 and I22, we see that my moment of inertia about the third axis will be I11 plus I22 from perpendicular axis theorem, right? And we see that all the other, again, because x3 is 0, we expect that I13 is also equal to I23. These are all 0 because the dimensions along the third axis OX3, GX3 will be 0. And finally, we expect that I12 is not 0 because there is no symmetry about C. So no symmetry. And we can find this specifically by using the formula summation m x1 x2. So that summation will become integral, so that will become x1 x2 times dm, the mass, and eventually we get that this is equal to m times ab. So I12 is non-zero. Okay, so then the second case, the second example that I have is when we have to find Ig in the set. So we have to find again from the previous example. So let me call this example 1. So in example 2, we have to find Ig in the set of axes, obtained by rotating axis G x1 x2 x3 about gx3, right? So that the new axis gx1 prime lies along the diagonal, Okay, so what we have is that we have a plate, and the plate, the new axis of rotation is along the diagonal. Again, the same plate of dimensions 2a and 2b, and we see that the new axis will make an angle. Let's say this angle is alpha. So the new axis makes an angle alpha equal to tan inverse b over a. And so my rotation axis will be, in this case my rotation axis will be, rotation transformation matrix will be cos alpha sin alpha and minus sin alpha cos alpha 0 0 1 0 0 1. And we see that Ig prime comes out to be, our transformed matrix comes out to be A transpose Ig A transpose, and whatever the moment of inertia was about one of the principal, let's say along point C, then we rotate. So Ig will be around the point G. So Ig will be the moment of inertia along the center of mass. Okay, so the point is G. Okay, so then we could The second part of the problem is, how about kinetic energy? If we were to find the kinetic energy of the problem, then how to do that? So suppose the plate in previous example, the plate in previous example is rotated about one of its diameters with angular speed lambda, and we need to find the kinetic energy. Energy of the system. Okay. So then again our kinetic energy will be, again using the formula, will be half omega transpose Ig omega, where our omega matrix will be, so this is the so if you had the angular speed lambda along let's say it is given along one of its diameters, then the corresponding omega matrix, taking into account that the diagonal makes an angle alpha, will be lambda cos alpha, lambda sin alpha 0, right? And my omega will be lambda cos alpha, lambda sin alpha 0, right? And this is what we have in Ig. So Ig will be our moment of inertia along the center of mass. Or alternatively, we could use the formula that omega is lambda 0 0, that is along the rotated axis, and then my Ig, my moment of inertia, will be replaced by Ig prime, that is along the rotated axis, and the answer will be the same as before. Okay, so the question now which comes is, how about finding the principal axis of rotation? How about finding the principal axis? Okay, so the principal axis, we have to find the principal axis of a symmetric tensor, right? So the goal is we need to find the transformation matrix A, A, such that A transpose TA, where T is my kinetic energy, is diagonal, right? So that is the place, that is the case when we expect the transformation matrices have columns which are the principal axis of the coordinate system. Okay, so then, so what we have is that so what is, okay, so then what we have is, let us see one more result in the form of a theorem. So the problem says that the result is on the orthogonal diagonalization. So the problem says, given any real symmetric matrix T, there exists an orthogonal matrix A such that ATA transpose is a diagonal matrix. Okay. So this question is how to find this A. So this question is, the idea is that to find this principal axis, we find the rows of this matrix. So if we were to find the principal axis, see, this is our original goal, and suppose we have already found this matrix A, which is an orthogonal matrix such that this sort of transformation is a diagonal matrix, then we expect that the principal axis will be the rows of A. So that is what I just said few minutes back. And then if we were to see what happens to the expressions for the angular momentum and the kinetic energy along the principal axis. So along the principal axis, we see that L0 is A omega 1 E1 plus B omega 1 E2 plus C omega 3 E3. Right? And we see that T will be half A omega 1 square plus B omega 2 square plus C omega 3 square, where my A, B, C are the principal moments. These are my moment of inertias along the principal axis. Okay. So then this question now is, if we can utilize some of the symmetry in the body to find these principal axes, right? So this is what we have. So how about finding the principal axis using dynamical symmetry? So the goal is we want to find the principal axis from the geometric symmetries, Okay, so then I'll just, in this topic of discussion, I'll just provide some tips or some rules which will allow us to find these principal axes just purely from geometry. So the rule one is that suppose a body has dynamical symmetry, has the so-called reflective symmetry, right? So reflective symmetry in a plane through O, and then the line through O perpendicular to this plane. Well, so we are talking about some sort of a symmetry about a plane, right? And O might be the center of the origin of the coordinate system, right? So then the line through O perpendicular to the plane is a principal axis. So then the second rule is if a body has rotational symmetry, let's say about an axis, then this axis is a principal axis. So we have a rotational symmetry, then we have a principal axis about this body. Okay, so then another thumb rule is, suppose there is an axis which is passing. So these are some examples here. So suppose we have an axis which is passing through the center of the uniform rectangular plate. Then the principal axis is, it has both rotational and reflective symmetry, and that axis will be the principal axis. Okay, so the example is an axis passing through the center of uniform rectangular plate. So so I'm talking about one of these axes passing through the center of a uniform rectangular plate. So we have both the rotational and the reflective symmetry here. And then another example is that of a uniform cone with with a pentagon as the basis, with a pentagonal basis, base, right? So we have a pentagon, right, and we have a uniform cone here, and we see that the pentagon's axis is going to pass through given the symmetry in the base, the axis where we have a where we expect that the axis will be principal axis will be passing through the center of the pentagon base, and it should go towards the vertex, right? So that is a natural choice of the principal axis. Okay, so this is the axis passing through G, through G, which is the center of mass, right? Okay, so then we can expect we can now categorize the various types of symmetries here, and then look at these specific cases. Okay, so the first case is different bodies with same principal axis, principal moments of inertia have the same motion, right? So we have three cases to talk about here. The first case is when A is not equal to B is not equal to C. So the first is this. So this is purely asymmetric body. So A, B, C are the moment of inertia of the body, right? So these are completely dynamically asymmetric objects. So for example, we have the case of a rectangular plate, right? So we have a plate here, and this is what we have with different dimensions along each of the axes, right? So we have different dimensions along each of the axes, and then in this case we expect the moment of inertia to be I11, which is A, to be 1/3 m a square, and similarly we can find I22, and using perpendicular axis theorem we can find the third moment. So using perpendicular axis theorem. Okay, so this is fairly straightforward. And then some other examples that we have is the case of when we have at least two principal moment of inertia is equal. So the second case is A equal to B not equal to C. This is when we have dynamically or axially symmetric objects about, let's say, about one of the axes OX3, right? So OX3 is the perpendicular to the plate, about OX3. So the point is, it is not necessary that OX3, this axis is the axis of revolution, right? So we expect that in a typical object, this third axis corresponding to the moment of inertia C will be along the axis of rotation. But we can have examples, for example, the case of a spinning top, where the top may precess about, not only rotate about this axis but also precess about this axis as well, right? Since this whole complicated motion of a top will be seen in the next module. So what I want to raise is that we have a contradiction, that the OX3 axis is the axis of revolution, and one example is that of a spinning top. Okay. So then the third case is when A is equal to B is equal to C, and this is the case of a dynamically symmetric or dynamically or spherically symmetric object, right? So in this case, the moment of inertia tensor is a scalar multiple of identity. And we expect that all three moments of inertia are equal. And in this case, it turns out that the principal axis can be arbitrarily chosen. So there is so much symmetry that we have lots of options. So arbitrary principal axis as long as they form a right-handed system. Okay, so then we have a third rule, which is rule B. So the B says that if we have if we have two different axes of dynamical symmetry. So if there is two different axes of dynamical symmetry, dynamical and axial symmetry through O, then it must pass through then it must be dynamically spherically symmetric objects, right? So if two or more axes which are dynamically axially symmetric, then it's a dynamically spherically symmetric objects. Spherically symmetric object. Okay, so some examples in mind are the so-called tetrahedron, right? So tetrahedron is one case. So there is one axis of symmetry along each of the face of the tetrahedron. So there are four axes of dynamical symmetry. So this is spherically symmetric object. So similarly we have four. So tetrahedron has four axes of symmetry. Similarly we have the cube, where we expect that we have six faces. So we have six axes of symmetry. And similarly we have pentagon, or this is called the pentagonal ball, right? So the pentagonal ball will have five faces. So we have five axes of symmetry, and so these are all spherically symmetric objects. So I think I'm all out of time here, and in the next module we will start with the rigid body dynamics corresponding to the motion, specifically gearing towards the motion of a spinning top. So thank you so far for listening.